Hey guys, here are your notes on section 5.1, day one. Section 5.1 is about composition functions and how we define them, how we find them, and what their domain is made up of. All right, so first of all, by definition, a composition function is when one function is plugged into another function. The notation that is used is either this or that. This looks like an open circle. Looks like it says fog, but it's literally read as f of g of x. And this means the exact same thing, f of g of x. It's literally one function inside of another function. So right now, the g of x function is inside of function f, okay? Well, what is the domain of a composition function? The domain of f of g of x is the set of all x values in the domain of g of x such that g of x is in the domain of f of x. Okay, so basically it's saying that the domain consists of x values that first are in g of x's domain, and then g of x has to be in the domain of f of x. And again, that can be a little bit hard to kind of understand. So let me just put it into a picture for you. So if you're looking at a composition function that says f of g of x, like these are, then think about it. What's actually happened, I prefer this notation, what's actually happening first is x is getting plugged into function g. With compositions, you kind of work your way from the inside out. So first, x is being plugged into the function g. So think about that. First, x is going to go into function g, right? And then g is going to spit out an output that we will call g of x, right? X goes into function g and it spits out g of x, the output. So now g of x, that output is what's going to get plugged into function f. So now g of x gets plugged into function f, and it is f of that input g of x that gets spit out, okay? So think about it. First, x goes into function g. That means x has to be in the domain of function g because that's where it all starts. X goes into function g first, so x must be in the domain of function g. Well, then g is going to spit out g of x. Now g of x becomes your new input. Now g of x is going to be plugged into function f, and f is going to spit out f of g of x. So if g of x is actually what's getting plugged into function f, well then g of x, that output, has to be in the domain of function f. So x has to be in g's domain. G of x has to be in f's domain in order for a composition function to work, okay? All right, well, there's a couple things they're going to ask us to do. First, they're just going to start off by asking us to evaluate it, and that's probably the easiest that it is to work with a composition. All right, so first they've given us, let f of x be the function 2x squared minus 3, and let g of x be the function equal to 4x. So in the first example, they're going to ask you to evaluate f of g of 1. Well, guys, I prefer the other notation that says f of g of 1. I just feel like this paints the picture a little bit easier. So if they're going to put a number inside of this composition, that's the easiest it's going to be. All we have to do is work with pure numbers. So essentially what's happening is first we have to take this input of 1 and plug it into g. So take it off to the side and find g of 1. If you plug 1 into function g, what comes out, right? Well, g of x is 4x. That would be 4 times 1. 4 would come out. So since g of 1 spits out a 4, 4 is your new input that goes into function f. So now in reality, we are asked to find f of 4. So now to find f of 4, I have to go to function f and plug a 4 in for his x, which would be equal to 2 times 4 squared minus 3. And then it's all about PEMDAS, right? We square first, that's 16. 2 times 16 is 32, minus 3, and 29 comes out. So f of g of 1 is equal to 29. Okay, and like I said, working with numbers is the easiest way to work with compositions. When they want you to work in terms of x, then you're strictly literally taking an entire function and plugging it into another function. All right. I'm actually going to leave these 3 examples to be filled in on the filled in notes that you guys can see when the pictures I send you, just to make the video shorter. So if you want to see these 3 examples, they'll be on the filled in pictures that I send you. Okay. All right. Let's go to the next page. All right. This one says, if f of x and g of x are polynomial functions, use the table of values for f of x and g of x to complete the table of values for f of g of x. So here they've given you a table of values for function g. So this is function g. So when you plug this value of x into function g, it spits out a 4, right? So this is g of -2, a 4 comes out. When you plug -1 into function g of -1, it spits out a 1, and so on. And then this is the table of values for f of x. These are all the x values that you will plug in, and then these are the outputs that will come out. So this is all for function f. So if you plug 0 into function f, f of 0, a 3 will come out. If you plug 1 into function f, f of 1, a 4 will come out, and so on. So now they want us to use these 2 tables to complete the table for f of g of x. Well, again, I like to think of it as this, f of g of x. So if x is -2, what is f of g of -2? Well, think about it. First, -2 would go into function g. So go to your g table. If you plug a -2 into function g, this table says a 4 will come out. So g of -2 spits out a 4. So now 4 is what you plug into function f. So go to function f and look for your input to be a 4. If you plug a 4 into function f, the table says that 7 will come out. So that means f of g of -2 ends with a 7. Okay, what about -1? What is f of g of -1? Well, if I plug a -1 into g, go to the table, if -1 goes into g, then a 1 would come out. So now g of -1 spits out a 1. So it's a 1 that's going to go into function f. So go to function f, look for a 1 to go in. What does it say comes out? A 4. So now a 4 would come out for f of g of -1. All right, what about 0? What is f of g of 0? Well, first 0 would go into function g. So go to g, find a 0 going in. What number comes out? 0. So now 0 is the number that would go into function f. So according to function f's table, if 0 goes in, what number comes out? A 3. All right, and then let's do 1. What is f of g of 1? Well, if 1 goes into function g, according to this table, a 1 will come out. So then 1 is what gets plugged into function f. So according to this table, if a 1 goes into function f, a 4 will come out. Okay, and then last, what about f of g of 3? Well, first that 3 would go into function g. So go to function g and look for a 3 to go in. Well, a 3 doesn't live as one of function g's inputs, which means that 3 must not be in the domain of g according to these tables. So if that's the case, if g is not a number that you could plug into, if 3 is not an x value that you could plug into function g, then it's not in the domain and it would spit out an undefined output because you're trying to plug a number into a function that is not in that function's domain. Okay? All right, perfect. All right, now they're going to ask you to physically find a composition function. So if you notice in the previous example on the first page, they asked us to find f of g of 1. So they gave us a number to replace x with. We were replacing x with a 1, and we had a starting point. Well, here they're not. They're asking you to find f of g of x. So in that case, x already lives inside of both of these functions. So we're literally going to have to take one entire function as is and plug it into another function. All right, because we have no value to replace x with. All right, but again, if they're going to ask me to find f of g of x, I prefer it to look like this. To me, this just makes more sense and is visually easier to understand. All right, so first, x would go into g, right? Well, x is already going into function g. We have that piece of information already. And if you notice, just take note of their domains, right? Because it's important that we're working with values that are in each function's domain. The domain of g of x right now is all real numbers, right? I can plug any number into this function. It's a linear function and nothing bad's going to happen, right? No dividing by 0, no negative numbers under an even root radical. Same thing here. The domain of f is all real numbers. This is a quadratic expression. I can plug any number I want in for x and nothing bad will happen. All right, so there's not really many restrictions that we have to worry about who can be plugged into what function. All right, well, if they're going to ask me to find f of g of x, like I said, x goes into g first. X is already living inside of function g. So really, g of x is 2x plus 3. So it's really f of 2x plus 3 that we are being asked to find. So in reality, I have to take this entire function, the g function, and plug it into function f. And if I do that, f of 2x plus 3, I'm going to go to function f, take all of his x's out, and plug a 2x plus 3 in for them. So x comes out, 2x plus 3 quantity squared goes in. And then plus 3 times the quantity, 2x plus 3 goes in for x. And then don't forget it ends with a minus 1. So now f of g of x is literally us taking the function g, plugging it into f, getting this expression, and now all we have to do is clean all of this up. And then that will be the new function we are left with, f of g of x. All right, so we're going to FOIL that out. That's a FOIL in disguise. I will get 4x squared plus 12x plus 9, distribute the 3, plus 6x, plus 9, and then minus 1 comes down. Combine like terms, I end up with 4x squared plus, looks like 18x's, 18 minus 1 plus 17. And that will be our remaining or resulting function, f of g of x. Okay, so that is your answer. And then the domain. Well, guys, if you think about it, first, x would go into function g. So x would have to be in g's domain. But g's domain is all real numbers, so there's no restrictions that I have to worry about, right? And then his output, g of x, would have to go into function f. But function f's domain is all real numbers. So there's no number that could possibly come out of this function that would not be in function f's domain. So the domain of your resulting function should be all real numbers because I had no restrictions to worry about to begin with. And if you look at this new expression that you're left with, nothing bad should go along with this expression when you plug a number in for x, right? So there's no restriction that would have to carry through, and there's no restriction with the end resulting function. So the domain, again, is all real numbers. So I'll just say all real numbers, or that would be negative infinity to positive infinity. Okay? All right, now they're going to ask you to find g of f of x, which is g of f of x. So in this case, you'll be taking the entire f of x function and plugging it into function g. Again, order matters. F of g, g of f, the answer should not be the same, right? Because you're not plugging the same function in the same order, all right? I'm going to leave this one for you guys to try, but again, it'll be filled in on the actual picture of the notes, okay? Just to save time on the video. All right, now, clearly finding the composition is extremely important, and knowing what the domain of that composition is important. So in the next couple examples, what they're going to ask you to do is, without finding the composition function, without finding the resulting function, can you find the domain first without seeing the composition function? Okay, so let's look here. So f of x is defined to be the function 1 over x plus 2, and g of x is defined to be the function 4 over x minus 1. Guys, let's take a peek at what their domains are right now. Looking at this function, we know we would never want x to be negative 2, right? We'd never want to divide by 0. So we know right now f of x has a domain where x would never be negative 2. And g of x definitely has a domain where x would never be 1. So sometimes it's nice to take note of what those domains are before you even get started, just to kind of have like a starting off point, okay? All right, well, they're going to ask you right now to find the domain of f of g of x, which remember is the same thing as f of g of x. So without seeing what that resulting function is, can you find the domain? All right, well, let's start at the beginning. First, x would go into function g. So x would have to be in g's domain, right? First, x goes into g, right? So x must be in g's domain. So in that case, what is g's domain? Because x has to be a part of it, right? So right now, how do I want to write this? Let's say, let's do this. Domain of g. The domain of G, we've already said, is that X can't be 1. So that domain has to carry through the entire time because that's where this entire composition function starts. It starts with X going into function G. So X would never be allowed to be 1 because he's going to start by going into function G. And we don't want X to be 1. All right, so we're going to hold on to that. That is definitely part of the resulting composition function's domain, the fact that X can't be 1. All right, now G of X is going to go into function F, right? So next, G of X goes into F. So G of X has to be in F's domain. Okay, well, what did we say is the domain of F? If G of X has to be in F's domain, what is the domain of F? The domain of F, we said, is that X can't be -2. Okay, but remember, it's not X that actually ends up going into F. It's G of X that ends up going into F. So in this case, it's not X that we don't want to equal -2. We want to make sure that the output from G of X, never equals -2. So take your G of X function, which is 4 over X minus 1, and we want to make sure that this never becomes -2. I never want the output of G, which will be the next thing that goes into function F, to be a -2. So G of X is 4 over X minus 1. We want to make sure that 4 over X minus 1 never results in spitting out a -2, because that would be the next input that goes into function F, and it's not allowed. -2 cannot go in. So I would just think of this as a cross multiply. Put this over 1 and cross multiply. -2 times this is -2x plus 2 equals 4 times 1 is 4. And then solve this for x, because that's the number that we then don't want coming out of G of x. Or function G, I should say. All right, so then we would get -2x equals 2, and x cannot be -1. All right, so if -1 is the resulting output from function G and then is asked to be put in there, I don't want that. I can't have that, all right? All right, so your overall domain of f of G of x is we never want x to be 1 or -1, okay? If I plug a -1 into this function, that means it's becoming a -2, and a -2 can't go into this function next, okay? So I hope that makes sense. And again, sometimes it's easier to when you're looking at the composition function itself, but they are asking you to find the domain without ever seeing this resulting function. So now this resulting function would have a domain of x not being allowed to be 1 or -1, okay? All right. Now, these are the hardest problems probably, okay? All right, look at G of f of x. Now they want you to find the domain of G of f of x. Well, again, I like to think of it like this first, G of f of x, right? So start from the inside. First, x would go into function f. So first, x goes into f. So we need x to be in f's domain because that's the first function x is going to go into. So x must be in f's domain. All right, well, if that's true, what is f's domain? So the domain of f, we said, is x can't be -2. So we're definitely going to hold on to that. You would never start by plugging a -2 in here because -2 can't go into function f. All right. Next, the output f of x is what's going to get plugged into function g, right? So now, or next, f of x, right, that output of f is going to get plugged into g. So f of x must be in g's domain. Okay. Well, what is G's domain? We said the domain of G is that X cannot be 1. But remember, it's not really X who ends up going into G, it's f of X that goes into G. So it's not really X that I don't want to be 1, it's f of X, the output from function f that goes into G. It's that I don't want to actually be 1. So really, it's f of X that can't be 1. And who is f of X? F of X is 1 over X plus 2. We want to make sure that 1 over X plus 2 never becomes a 1. All right, so 1 over X plus 2 can never become a 1. All right, so now let's solve that for what X value does make function f becoming a 1, because that's really the X value that we never want to use in this composition function. All right, so again, let's put it over 1. Let's cross multiply. I'm going to get X plus 2 equals 1, and you find out that X cannot be negative 1. Okay, so now you find out that this composition function, g of f of x, cannot be negative 2 and it cannot be negative 1. All right, so again, the overall domain is that x cannot be negative 2 or negative 1. All right, those are x values that we cannot work with this composition function, right? X goes into f, so x can't be negative 2. F of x goes into G, so I never want f of x to be a 1, and it would take a negative 1 to make f of x spit a 1 out, so those are the two numbers that you would never want to work with in this composition function. They would not be in its domain. All right, so now that's how you find the composition function's domain without ever seeing the actual composition function itself. So now the last two examples, now they ask you, all right, now that we know what their domains are, now I actually want you to find f of g of x. So guys, in part A, we found the domain of f of g of x, and it said x can't be 1 or negative 1. Now they actually want you to find the composition function. What would the composition function look like between these two functions? And then watch, once we find it, I'll prove to you that these really are not in that function's domain. So now we're actually going to find f of g of x, right? So f of g of x. We're going to find that composition function. So we're going to take x and plug it into g, but remember, x is already living inside of function g. So then you end up taking the entire g of x function and plugging it into f. So really we'll be finding f of, what was the g of x function? The g of x function was 4 over x minus 1. So we're going to take that entire function and we're going to plug it into function f. So let's do that. So what is function f? If we're going to plug 4 over x minus 1 into function f is 1 over x plus 2. So we have to take this x out and plug this entire function in for that x. So it'll look like 1 over, take x out, put 4 over x minus 1 in, and then we still have to add that 2. Okay, all right, so we have just plugged the entire g of x function into function f. Now we got to clean it up, right? We have a complex fraction, we have a fraction within a fraction. A couple different things you can do here. Right away, I'm going to look to get rid of this complex fraction down here. So I know timesing by his denominator would work, but I can't just do it to one piece. So I'm going to times the entire denominator by x minus 1. And then if I times the denominator of a fraction by x minus 1, I got to times the top by x minus 1 as well. All right. Well, on top, x minus 1 times 1 is x minus 1 over x minus 1. It's almost like you're distributing it to the denominator. X minus 1 times this fraction, the x minus 1s would cancel, and you would just be left with 4. And then x minus 1 times that positive 2, you have to distribute the positive 2 to the x minus 1, right? So you'd end up with positive 2 times x is plus 2x. Positive 2 times minus 1 is negative 2. All right, so you're basically just distributing that x minus 1 to the bottom. All right, then that becomes x minus 1 over, the bottom will clean up to 2x plus 2. right? And just for simplification purposes, I'm going to factor out the GCF at the bottom, x minus 1 over a 2 and an x plus 1. So there is your resulting composition function. And again, these are equal. I've just simplified this one a little bit. All right. So now if you look, this is the composition function, f of g of x. And you can look right now at this function and know who would you never want to plug into it. I definitely don't want to plug in -1, right? All right, so we definitely know that. But we already said f of g of x has a domain. Let me go back over here. The domain of f of g of x, we already said was 1, x can't be 1 or -1. Well, we've gotten the -1 covered, but why did that 1 come into play here? Well, the reason the 1 comes into play, and the reason you can't see it right now is the reason 1 can't get plugged in, is not in his domain, is remember where this function starts. He starts with an x going into function g. So you have to hold on to that domain from the very, very get-go. If there is any type of restriction on g's domain, it's going to carry through the entire problem because that's where this problem starts. It starts with x going into g. So what is g's initial domain? X can't be 1. So we're always going to hold on to the fact that x cannot be 1 right from the get-go because that's where this composition function starts, right? And then it's g of x who can't go into f. But luckily, the g of x can't not being able to go into function f, we usually get that restriction at the end of the problem. You'll be able to cover your bases, all right? Where we had to here, we had to do all of this. All right, well then g of x has to go into f, so g of x has to be in f's domain, so g of x can't be that -2, and that's how we found out that x can't be -1, and so on. Again, usually you get that one. You can see it from the ending result. All right, it never hurts to check, but you always have to hold on to any of those first restrictions on that inside function, and that you will not most likely get when you look at the end result, okay? All right. All right, so then the last one is they want you to find g of f of x, right? Now we already know his domain is that x can't be -2 and -1. So now they actually want you to find that physical composition function. What is the actual resulting function? We already know its domain. What does the actual function look like, right? So g of f of x. All right, so first x would go into function f, but x is already living inside of function f. So in reality, it's f of x, the entire function, which is 1 over x plus 2, that is going to get plugged into function g. All right, so let's do that. So let's plug 1 over x plus 2 into the entire g function. So the g of x function says this, 4 over x minus 1. So that x is going to come out, and the entire f of x function is going to go in. So that's going to become 4 over x comes out, 1 over x plus 2 goes in, and then you still have that minus 1. Okay? All right, and then again, it's just about the cleanup. This is a complex fraction. We have a fraction within a fraction. So I'm going to do the exact same thing I did before. I'm going to times the denominator by x plus 2 to work on getting rid of that complex fraction. But whatever I do to the denominator, I have to do to the top, times that by x plus 2. So just for now, I'm going to do 4 times x plus 2, and I'm not even going to distribute it. I'm just going to write them as multiplication together. All right, over, if I do a distribution again, x plus 2 times this fraction, the x plus 2's would cancel, and I'd be left with 1. And then x plus 2 times -1, I actually end up having to distribute the -1 to the x and the plus 2. -1 times x is -x. -1 times +2 is -2. And I end up with 4 times x plus 2 on top over a -x minus 1. Okay? All right, well, again, just for simplification purposes, I'm going to factor out that negative sign, and I'm going to get 4 over x plus 2 over -x plus 1. All right, so this is your composition function, and I can clearly see that I definitely don't want x to be -1. Look at that. We would never want x to be -1 going into this composition function, right? I can see that from the resulting function right there. However, think about how this function started. It started with x going into function f. So you would never start with a number that is not in f's domain. And what is f's domain? F's domain is that x can't be -2. So we're going to have to hold on to that restriction the entire time. Okay? And then again, and then it's f of x. that has to be in G's domain. So we would never want f of x to become a number that is not in G's domain. But normally, by finding the composition function, you can cover your bases by using that end resulting function to worry about that part of it. I don't have to worry about f of x, not being in G's domain, because it should be taken care of with the end resulting function. Before, I had to do all of this because I didn't have an end resulting function to look at, all right? But again, it never hurts to double check. You would make sure that if f of x has to go into G, I would never want f of x to spit out a 1, because 1 is not in G's domain, all right? But here we are. We've covered our bases. We said that the domain of G of f of x is that x can't be -2 or -1. And I've just proved that yet again, okay? All right. The domain can be definitely a little bit confusing, so please feel free to reach out to me if anything is not making sense. All right. Otherwise, you do have a homework assignment on these problems, and good luck.